Good morning and good afternoon and good evening, everyone, and welcome to our next installment of our Ask the Expert series, which today is focused on our RGA technique. Our expert today is Dr. Jayesh Kumar Das, Senior Principal Scientist and Operations Manager for Thermal and Gas Analysis here at Eurofins EAJ Laboratories. I am Dina Ingram, and and I am the marketing manager. Um, sorry, like for this event today. Prior to getting started, I would like to go over a few housekeeping items with you guys. First, all all attendees have been muted. However, if you have more questions um, during the presentation, please share them in the questions panel, which is located in the bottom right corner of your screen. You may send these questions at any time during the presentation. And if time permits, we will answer these questions during the webinar. And if not, we will follow up with you in the coming weeks. Lastly, at the end of the presentation today, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now, I will turn it over to Frona P. Wilson, who is the RGA Director, who will be moderating today's presentation. Frona?
Thank you, Dina, for the introduction. Hello, everyone, and thank you for joining us for Ask the Expert Residual Gas Analysis webinar. As Dina said, my name is Frona Wilson. I've worked in the RGA business for many, many years, first with Pernica Corporation and now with Eurofins EAG Labs. We're going to start with a brief introduction about EAG, some history of RGA. I will introduce our expert, and finally, getting to the good part, answering your questions. Eurofins is a global leader in testing with more than 58,000 employees and 900 laboratories in 54 countries. EAG is a division of Eurofins, specializing in materials testing with over 40 years experience. We have more than 600 employees in 20 laboratory facilities all over the world. These laboratories include more than 2,500 different types of testing equipment and support for over 5,000 clients. Our highly skilled employees use industry-leading, state-of-the-art technology and take advantage of scientific and engineering know-how to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. We have two RGA laboratories, one in Syracuse, New York, and another in Eindhoven, Netherlands, which are highlighted here. If I had to describe EAG Labs with two words, it would be problem solvers. As highlighted in this flowchart, EAG helps to solve commercial challenges from concept all the way through a product's life cycle. Client success requires control and optimization at all stages. We can help you with R&D, prototype development, pilot studies, manufacturing, reliability, and failure analysis. EAG provides the knowledge and appropriate tools to help clients faster and better. But today, we're all about residual gas analysis. RGA is one of the smaller, more unique testing techniques offered at EAG. It's also known as internal gas analysis and was developed in the late 70s by a group of scientists for the military and space community as a tool to ensure reliability in electronic components. Today, it is known as MIL Standard 883-750 Test Method 1018. John Pernica, the founder of Pernica Corporation, designed and manufactured one of the first instruments to perform Test Method 1018. EAG acquired Pernica in 2018, and the RGA lab now resides at the Eurofins EAG Materials Science location in Syracuse, New York. I've been asked many times, why did you move the lab from Colorado to New York? Well, the reason is the New York facility has been the center of excellence for testing an extensive variety of materials, including ceramics, semiconductor, and metal alloys. This location has been providing testing for more than 20 years and has dedicated teams of thermal and gas analysis that are the perfect complement to RGA. On that note, I'd like to introduce you to our expert, Jayesh Kumar Das. Dr. Das is the operations manager for the thermal and gas analysis teams and is our senior principal scientist. Prior to joining EAG, he worked on extensive NASA projects, and in 2018, joined our team to focus on providing technical support for existing gas analysis testing and developing new gas analysis techniques. So now let's ask this expert some questions. Jayesh, are you ready? So the first question is 3 little words, but it probably has a big answer. What is RGA?
Thank you, Frona, for the nice introduction and setting up the tone for this today's special event. And yes, this is the question that we would like to start with. And let's delve into the detail of this. So RGA is just an acronym for residual gas analysis. But if you look into the detail of it, it is a mass spectrometer system, which is a part of an ultra-high vacuum system, so where you analyze the gases. Now, the main mode of analysis here is when you introduce a gas into an ultra-high vacuum chamber, ionization is performed through the mass spectrometer system, and the ions are then measured to look by the mass spectrometer to first identify as well as quantify the different gas species. Now, what are the major applications? The simplest quadrupole mass spec system with low resolutions, they are used for monitoring the gas composition in a vacuum system, or where you want to monitor the gas quality. You can use the high resolution mass spectrometers for qualitative and quantitative analysis, the one that we have for RGA setup at our EAG laboratories. So this particular RGA is designed to do internal gas analysis for hermetic devices. The meaning of hermetic device is that it has a cavity and it is a sealed cavity, so there is some kind of a gas environment or sometimes a vacuum inside the cavity. And we want to confirm or want to investigate what is the gas inside this cavity. And that's why this RGA system is developed, where we can extract the gas from the cavity and look at their composition, identify and quantify these gases. And as Frona said in the earlier, this technique was developed in 1970s and especially converted into a very specific test method called MIL Standard 883-750 test method 1018. Now this test method is defined in a way that it became over the year become a gold standard for hermetic device, which are microelectronics devices as well as medical implants. And we have to follow that test method when we are doing a MIL standard testing. But for some other reason, if we deviate from those test method defined parameters in that test method, then we would term those testing as commercial testing. For example, when we are doing medical devices, the device may be at the temperature of 40 degrees Celsius, closer to the body temperature, and which is a deviation from the mill standard. Because in mill standard, the entire testing is done at 100 degrees Celsius. The sample is at 100 degrees Celsius. The mass spectrometer system, the vacuum system, the entire chamber is at 100 degrees Celsius, and we cannot deviate from that. But when we do medical device with some kind of an exception, then that will be termed as commercial testing. So RGA in general is a gas measurement system, and it can be developed into a different, very specific kind of a test measurement system. But the core of the RGA system is a quadrupole mass spec system working in ultra high vacuum. So I think that would probably give a little bit of idea on what is RGA in general. So so we will
Sorry,
go.
I
Yeah,
was muted.
yeah.
These next two questions were submitted by our viewers, and I think they can probably be answered together. What are the components of the RGA system, and what is the function of each component in RGA testing?
Yes, and let's start with some simple schematic here. So as I said, the quadrupole mass spec system, which is into the schematic somewhere here in section 3, and it is surrounded by a lot of arrangements to make our test method meaningful. So that's why, to make this complex diagram into a little bit of simpler way, what we did is divided into 3 sections, 1, 2, and 3. The first section mainly deals with the calibration of the equipment. So as you can see, in the lower part, we have first component that I would describe is the moisture generator. Now, what is the role of this? What is the function of this component? It is generating a known amount of moisture with a nitrogen mix. So nitrogen is supplied to this generator, a moisture generator, and a moisture is added into this unit, and final mix of moisture plus nitrogen is supplied to the valve system here, and that goes towards the volume calibrator. Now the moisture generator has this inside a permeation tube, NIST calibrated permeation tube, which is emitting the moisture at constant rate. And by changing the flow rate for nitrogen, we can change the concentration of moisture into the final gas that is coming out of this generator. So this moisture generator is calibrated annually or as and when required, and it can provide very highly stable gas mix that we can use for our calibration. Now, once it goes to the valve system, we can control the flow there, and then it goes to something called volume calibrator. What is the function of this segment or this section? Is that it has a special arrangement of valves where we can introduce known amount of gas to the sample chamber, which is in the section 2 here. So the volume calibrator has different volumes on it, like 10 cc, 1 cc, 0.1 cc, and 0.01 cc. So I can introduce the standard volume of gas into the sample chamber using volume calibrator. However, if you look at carefully, that entire gas line is connected to volume calibrator as well as forwarded towards the hygro computer. Hygro computer is another independent device that measures the moisture into this gas. So the moisture generator is generating nitrogen and moisture for us, and it is calibrated, and so it is giving us a known amount of moisture, but we are required to independently measure moisture into the mix that is being introduced to the sample chamber. So the hygrocomputer's function is to confirm that what is the moisture content into the gas being submitted or gas being exposed to the sample chamber. And for mill standard, we have to do a daily calibration of 5,000 ppm plus or minus 500 ppm moisture needs to be introduced in the sample chamber. And for almost every volume, we have to calibrate daily prior to running our tests. Now, what we have done is that we have put a stricter criteria in here. Instead of 5,000 plus or minus 500 ppmb, what we do, we put 5,000 plus or minus 100 ppmb. So we have a narrower range of qualified gas that we will be supplying to the sample chamber. So that explains section 1. Now let's move to the section 2, where the heart of the entire system is the sample chamber, and it is connected to one part is sample port, another one is the volume calibrator, as we talked, and it has an independent barometron, which is a capacitance manometer pressure gauge system to measure the gas pressure inside the sample chamber. Beneath the sample chamber, we have two valves, which is isolating the vacuum generation arrangement. So we have a turbo pump and a bypass line that goes to a dry scroll pump, which is nothing but a scroll pump without any oil or any kind of a contaminant, and that would support the bypass line as well as also the turbo pump. We have a unit called IG1, which is an ion gauge, which measures the pressure in the range of 10 to the power minus 8, minus 9 torr. So that's the function of section 2. And let's talk about the sample port. So sample port is where we attach the sample to a mechanism where we can puncture the sample. And while loading the sample, what we do is generally close this valve so that the other system remains isolated and remains at the lower background of the gas. And then the sample port, once the sample is mounted, then the sample port valve and the bypass valve, which is just directly on the left side of the sample chamber here, they are open, and we attend the rough vacuum first. And once it is done, then we move to the turbo pump system to get a better background. We will see a little bit more detail in the later slide. Now, the third section is where the mass spectrometer is, and the mass spectrometer is under the isolated volume, and there is a valve between section 2 and section 3, which keeps the mass spectrometer always isolated from left side of the unit. And because of that, the mass spec volume is ultra clean, and it is always 24/7 pumped through the turbo pump and same kind of a dry scroll pump system. And normally our mass spectrometer is in the range of 10 to the power minus 9 and 10 to the power minus 10 torr kind of a pressure is into this region. And that is monitored by IG2, which is ion gauge 2. And we also monitor these values when we introduce the sample gas to the mass spec. The change into the IG2 is critical for us to confirm that we are actually analyzing the sample gas. So I would like to show next slide where we can see that. So maybe I will go back here. Now, let's say if I want to calibrate the mass spec for 5,000 ppm of moisture. So I would generate that 5,000 ppm plus nitrogen mix and introduce to the mass spec. But before doing that, what I have to do that, I have to make sure that my sample chamber background is acceptable and is in the range of being used. So what we do, as you can see here, first 5 scans are, so 0 to 4, first 5 scans are taken when these two valves are closed and V2 is open. So sample chamber is into this region, and we are looking at the background of the mass spec, background of the sample chamber, including the mass spec volume. Once that is done, then there will be an interactive window asking us to introduce the gas, the standard gas to the system. And once we do that, it will start the scanning, and we will go for, here you cannot see, but we go for another 20 scans. So 5 to 24. And that time you can see the increase into the signal. That's because we introduced the gas. And this is how we can do the analysis, either calibration, or in case of sample, what we will do, we will, same way, we will take the background and then we will puncture the sample while this valve is open. And that, as soon as you puncture, the gas will be introduced to the sample chamber. And by analyst, when they say proceed, it would open up the valve V2 and the gas would be transferred to the mass spec system. So this is how the individual components can be described for RGA system, and they have, each component has a very specific role to play, and they are like counter and balances to make sure that the test method is being followed and all the data being recorded. I would just like to confirm, I would like to emphasize on the fact here that the software is built by us, EAG, and this particular software is to control the mass specs. All the valves that we have discussed, these are automated and can be follows in a sequence of the test method to minimize the error on the part of manually operating the valve or forgetting to open something, and to avoid those, the entire system is automated.
Thank you for that wealth of information. We have more viewer questions. This one came in prior to the webinar. Is this a new RGA system for EAG, or is it the same Pernica RGA system that EAG acquired a few years ago?
Yeah, so I think as Prona discussed in the beginning, that we acquired Pernica Corporation in 2018, and this was the first mass spec system built for doing mill standard testing, and almost 20 to 30 years before we acquired. And our goal is to create a modern system. So what we did, I have an extensive list here, and let's see if I can explain some of the things in a little bit of more detail. So in this table, on the left column, the first column gives you what we had when we acquired the Pernica Corporation. So this particular RGA 166 is the unit that has been modernized or upgraded. And the first thing what we changed is the analyzer from Pfeiffer vacuum, which is QMG 422, but when now we have QMG 700, almost 3 generations of development in that controller, which is the main controller that controls the mass spec system. And the second thing is also the hydro computer. What we did is that we moved to a newer generation hydro computer, which are readily available and easy to maintain. And also we were also taking care of the parts which are obsolete, still in operation, but doesn't have any technical support. And we wanted to get away from those kind of parts, and that's the reason we moved from the earlier generation of analyzer, mass analyzer, as well as the hydro computer. We also went into the special method of moisture generation. Earlier, it was done manually by mixing dry or wet room air. We moved to our NIST calibrated Kintex system, where we can generate very high stable gas mix for our moisture generation in the morning, every day, daily, for the daily calibration. As I briefly said, we got away from the vendor software, which was not useful at all for doing the mill standard. It was good to analyze the mass spectrum, but as you can see from our software, we wanted to have a sequential test procedure followed on this instrument, and that's why we indigenously built the software. Also, we have an independent data analysis and reporting software which ties up well with our internal LIMS system at EAG, where we can track each job, each sample as soon as they enter the EAG facility. There are big changes into the vacuum system. We had oil pumps and old turbo pumps which were water cooled. We removed them. We put scroll pumps which are dry. There is no oil in those pumps. We also moved away from the water, the chiller part. We don't have to maintain them anymore. Our turbo pumps are air cooled, and some small changes while we were doing these bigger changes to generate a highly stable and a reproducible signal strength onto the mass spectrometer system. So the answer is yes, it is. If you We didn't change the number of the mass spec because that's we want to follow that, but we have changed almost all the component into the mass spectrometer to make it modern and also being controlled by a new generation software. So we can say that it's the same mass spec but highly upgraded and automated.
Thank you for all that information along the lines of RGA and software. The next question from a viewer is, what is the RGA detection limit?
Yes, we get this question a lot from our client, and I think this is a good time to attend that. So the first thing is that the RGA detection limit is controlled through the signal to noise ratio into the mass spec. Now, what is signal to noise ratio? So first, as you have seen, we have taken that 5 background scans, and then we are introducing the gas into the system. So that 5 background is giving me the background signal strength into the mass spectrometer system, and ideally the signal from the sample gas should be above that background, or let's say noise, into the mass spec system. So signal to noise ratio has to be positive, it has to be higher than 1. Now in this particular, this is also a part of our software, data processing software, and here I'm showing the example of the moisture calibration that was done yesterday. And as you can see, these are the different gases being measured into the mass spectrometer. And what we introduced is basically a mixture of nitrogen and moisture that you can see into this table here. So 5000 ppm plus 100 plus or minus 100 ppm and nitrogen mix. So this was introduced to the mass spectrometer, and you can see for moisture, the signal to noise ratio is around 40, whereas for nitrogen, the moisture it's very high because nitrogen is a very high signal here. And all other gases are below detection limit. Now, let's take the example of helium, where the signal to noise ratio is around 1.78. So there is an increase into the helium when we introduce to the mass spec, but that is not above 20. Now this 20 is the limit given by the mill standard. So in order to consider a gas that is above the detection limit, you have to have signal to noise ratio above 20. And as you can see in this, that most of the gases doesn't cross across. And we normally put the 100 ppm as our detection limit for the reporting purposes. And if anything measured below 100 ppm, it would be shown as below detection, as you can see in this table. So this is the little bit of information on how the detection limit can be determined. On top of that, what I would like to add is that this detection limit can be optimized based on individual gases. For example, for fluorocarbon, our detection limit is 50 ppmv. So we can measure anything above 50 ppm. But if we have the specific calibration for that gas, that we can also go into the 10 to 30 ppm level of measurement. The another challenges could be, because it is all controlled by the background signal, we are Our mass spec has an inbuilt memory effect for nitrogen. So nitrogen is always being introduced into the mass spec. Even the atmosphere has the nitrogen 78%. So those nitrogen or oxygen, those gas has some inbuilt background generated into the mass spec. And if we have to work on those detection limit, if we have to measure nitrogen less than 100 ppm or 50 ppm, we have to um, season our mass spec for that kind of environment. We have to get ready for that. But in general, for other gases, we have successfully achieved 50 ppm of detection limit for most of the gases.
Thank you, Dr. Das. Our next question, also from a viewer, does RGA need calibration for specific gases individually? You kind of answered that already, but I'll let you
Yes.
go into it further.
Yes, yes. I think yes, we need to calibrate. That is definitely a requirement. And let's discuss a little bit more into that, like why we are doing it. So first of all, on this left side, you can see the table that is our typical report would look like. I will focus on this area where we have these are the gases: hydrogen, helium, methane, moisture, nitrogen, carbon monoxide, oxygen, argon, carbon dioxide, total hydrocarbon and organics, fluorocarbons, ammonia, and the noble gases. These are all reported part of our standard report. And we have to calibrate each gas separately. So for hydrogen, we use hydrogen and nitrogen mix, and we acquire the gas standards from the third party certified gas standards to do that. And we do this calibration quarterly or as and when required. If we see that the hydrogen or some other gases are not as the expected values as considered by the client or considered by some other implications, then we would definitely calibrate the system on the same day using the standard gas. Ideally, they are required to calibrate every quarter. And moisture is, we calibrate for moisture every daily calibration prior to analysis. Now, so how this calibration, this individual calibration gives me the calibration factor for that particular gas. But it is not only limited to that, it is also being used to figure out, to actually quantify the interference and contribution to the other masses. I would like to show the example of moisture here. So when you introduce the moisture into the mass spec, and as we talked earlier, the moisture will be ionized. And when you ionize the moisture, you will have fragments of it. And this NIST mass spectrometry database is showing moisture would have like mass 17, almost 20% of contribution of mass 17, and less than 1% contribution for 16, 19, and 20. Now, mass 18 is the mass that we will use for determining the moisture content. But for example, if I have to find out the ammonia content into the same gas, then I would be looking at mass 17. But moisture would interfere, also generate mass 17. So how do I calibrate for that? And we use the moisture calibration for that. So what we determine that without any ammonia into the standard gas, which is my daily calibration, I would find out what is the contribution of moisture on mass 17, and that contribution factor will be used for determining ammonia. So the ammonia determination is based on the measured mass 17 minus, subtract the contribution from the moisture, and the leftover signal can be assigned to ammonia. So that determination is also made through the calibrations. Now, this is just one example, but there are several examples, several other gases that we have to figure out. And there is a complex method of deconvoluting these masses and their numbers. So, and that's why the calibration is probably the most critical part for RGA analysis. And yes, so the answer is yes, we have to calibrate for each gases, and also we have to look for the fragments which could also interfere with our assessment of that number for that mass. So we have to correct for that one too. So the calibration needs to be done in for that gas as well as other gases also, to confidently reach to the conclusion that my final numbers are free of any interferences, and based on the calibration data we can calculate this.
Thank you. So our next question, also from a viewer, what is the minimum volume of sample needed for RGA? What is the size of cavity? What size of cavity is minimally needed to measure the gas content?
Yeah, so here this is the suitability letter from DLA, which is giving us the range of volume from here 0.01 cc to 20 cc. So this particular RGA system is suitable to measure the sample which has the cavity between 0.01 cc to 20 cc. Now, the technical part of is that we have two constraints here. First, I need to have the volume calibrator that can provide me a volume in the required range. So if we have to move out of this range, I need to build that special volume calibrator, which is probably easier task. The more difficult task is that to figure out going back to the signal to noise ratio. So if I put low amount of gas, can I still maintain signal to noise ratio above 20? If I can do that, then I would be able to do lower volume. So in that case, one has to consider the limitation of the instrumentation. But right now, to answer the question, we can do any cavity which is above 0.01 cc and less than 20 cc. Yeah.
Thank you. So this is a question that we often get from clients, and I'll let you answer it, Dr. Das. How do you read and understand a typical RGA report?
Yes, I agree with Frona. It's most of the time we get the question on that, and I think this is the good time to give some more details on how to read rather the reports given from RGA. So this is our standard report format. What you would see, what you would get. Normally we send PDF file, and I would like to divide the report into three sections here. So the top part of the section contains the client information, which is the name of the client who has submitted, the company's name, and then EAG job number, which is a LIMS number into our system. Through that job, we can track the status of the job, the sample status, all different aspects of a job can be tracked down by that particular job number. Very critical for all the people internally working and related to this job, as well as for the client to inquire the status about the job. In case PO number is self-explanatory, as well as the total quantity of parts. So like if you are submitting 5 parts, 15 parts, like that. The lower part of the report contains the first top part, which is I have magnified here, contains the information regarding the test. And so if you have more than 2 samples, you would have another column. So my first column would remain same, but you would have second column here for the next sample. And it lists the details of the analysis. So it gives the timestamp when exactly the time analysis was done, analysis method. And here, this is the example of R-mill, which is RGA for mill standard. If you are submitting a sample for commercial testing, so deviating from the mill standard, it would read RCOM. And we have only 2 test methods in our reporting system, so either RMIL or RCOM. The sample ID, which is our internal ID, and it is just like our LIMS number. All the samples have very unique ID into our system, and that's where we can track each sample into our physically where it is in the location, and that has nothing to do with your ID or your serial number. That comes under part number and serial number information of the report. And military parts have date codes, or some other parts also have date codes, that if that is available, that would be also put into this category. This is the question that we often get, is what is this inlet pressure? So going back to the individual component where I defined, the sample chamber has this barometron pressure gauge, which is measuring the pressure into the sample chamber when we puncture the sample or when we introduce the calibration gas. So that is the pressure read into the sample chamber just after the background check, 5 scans, and just after the sample is introduced into the gas, into the system. So either I puncture and the gas goes to the sample chamber, that's the change. Before that, the sample chamber is sitting at 10 to the power minus 8 torr range, and this torr 2.86 in this particular case is showing that when I punctured the sample, this much of gas was introduced into the mass bag. Now there is a little bit of confusion can happen. Sometimes people think that the inlet pressure is the actual pressure inside the sample. That's not the case. When we puncture the sample, so imagine a sample volume and the sample chamber volume. So when I puncture, both the volumes get equilibrated, and this is the total volume of sample plus the sample chamber. So the inlet, it means that the sample, inside the sample, the pressure would be much higher than the inlet pressure here we are seeing. But this is but our sample chamber is at constant volume, so we can estimate what is the actual volume inside your sample. So this inlet pressure is a critical kind of a quantity for us to understand what kind of calibration factor we need to use, because our calibration factor is based on the standard volume of the gas, and depending on the pressure, the volume of the gas changes and the calibration factor, set of calibration factor would change. So we monitor that for each individual sample. The next item on that report is inlet temperature. In this particular case, it is around 100 degrees Celsius because it's a mill standard. If there is a deviation, we have, when the software would automatically reflect that into a problem, and the report cannot be generated until a subject matter expert look into it. So those are the part of the report generation checks and balances into the system. But inlet temperature is the temperature where sample is sitting. Our sample is mounted on in a way that the temperature head or a heater is touching samples directly, and that's where the temperature measurement is done, and that is given as inlet temperature. We also monitor instrument ID and the analyst, initials of the analyst who did this analysis. In this case, it's me. The lower part is where you are interested most, where we are putting the gas analyzed into the volume percentage. And we also have at the bottom, there is a conversion from volume percentage to 10,000. So 1 volume percent is 10,000 ppm. And that conversion is sometimes useful because when I say 5,000 ppm of moisture, that is basically 0.5 volume percent. Now in this particular case, we are talking about 6,258 ppm of moisture. We also get some questions that what is the volume percentage versus ppm? Is it a standard, or how to look at it? There is no standard on that. Basically, the unit are changed. When we are talking about very small amount of volume, we should be talking in very small amount of gas, we should be talking in ppm, whereas higher amount of gas could be said in volume percentage. For example, oxygen here is almost 2 200,000 ppm, which is doesn't make sense in like, it makes sense, but it's not very usual to say. So we say 20 volume percent of the gas, but here we could say 6,000 ppm of moisture. So it's a conveniency, but there is no difference between volume percent versus ppmv, and that's why we put that information at the bottom of the report. And there are some other at the bottom you would see report date. So normally report can be generated later part of after the analysis. So we also want to record that. So you would see that information also into the report. So, and there's a option for adding comment when somebody is reviewing the data, and in the comment section you would see if some other information which is critical for your understanding of the report, that would be also added into the comment. We also provide a supplementary data if you would like to understand your data in more detail. So apart from the standard report structure, we have another way of providing supplementary. On request, we can create a special report for you. And I would like to add that when we moved from Pernica to Syracuse, when we had a chance to build a new instrument, what we also did is that in the software we added a feature where after 20 scans the gas is still there into the mass spec, and we thought that why to waste that gas, and let's look at the entire spectrum of it. I would like to show the example here. So this is an example where I'm not showing the entire scale, but what we do, we start from 1 ppm 1 AMU mass unit to all the way up to 140 AMU. So what we are looking is that instead of looking at individual peaks of certain masses, what we are doing is running the entire spectrum, entire scan of the gas, leftover gas into the mass spec. And why we are doing it? Because we are only measuring the calibrated gases. But what if there is some unknown gas? What if something is not as expected? So have that kind of another set of eyes on our gas. We do this 1 to 140 AMU scan at the end of each analysis, including calibration, including samples. So if you want that information, we have that, and we can provide that as a supplementary report. In this particular gas, as you can see, we have measured argon and helium combination. It's a standard gas for helium and argon that we have analyzed, and 4 helium peak is seen, as well as 40 argon, which is a primary argon peak. But you can see the 40 argon, when doubly ionized, the mass to charge ratio falls around 20. So we can see that secondary peak for argon. One has to be very careful on that it cannot be interpreted as 20. And this is the calibration that we used, that we know exactly how much 20 mass 20 is coming from argon when we are putting argon as and then how to calculate neon gas.
Thank you for that very detailed step-by-step interpretation of the data sheet. We are running low on time, so I think we have time for one last question. This also came from our viewers. What other gas analysis capabilities do you offer at EAG?
Yeah, this is a good question, and let's see if I can move to the next slide. Yes. So as said from earlier said, we have another RGA facility at Eindhoven, and Eindhoven facility is optimized to do analysis inside the light bulbs or inside the gas bubbles. So if you have uh, a bubble inside a glass, Eindhoven facility can do that, and it's a very specialized, very optimized method, and they focus on that kind of analysis in addition to the regular RG analysis. But here at Syracuse, the thermal and gas analysis division can be subdivided into 3 different parts, where gas analysis for hermetic devices, where we discussed today this residual gas analysis. We also have a leak testing capability where we can look at the very fine leak into the microelectronic devices in the order of 10 to the power minus 10, minus 11, minus 12 range of leak can be tested using CHLD, which stands for cumulative helium leak detection. And then we have a separate department of a long list of instrumentation available on that for thermal outgassing. So we use this for a lot of failure analysis, as well as when we want to understand the thermal stability of a part of powder of or any kind of ceramic, or even the getter material or the epoxy being used for as an adhesive, all can be tested into this department by using variety of methods like evolved gas analysis. We did a webinar on this, and there is good information on this particular technique. We also have TGA and DSC method, as well as we have a direct insertion probe method. We have also recently added a method where we can analyze the surface area for the powder. The other segment of the thermal and gas analysis is related to the carbon, sulfur, nitrogen, oxygen, and hydrogen analysis. This is mainly done for solids, powders. And the good example for this community could be like if you are interested in knowing the hydrogen content into covar material, then these methods can be used, and the detection limit is exceptionally well here. We can measure hydrogen into the range of 2 to 5 ppm into a solid, and so that all capability makes a very, very strong base for doing anything related to gas analysis. Not only the final product, but if you have a failure analysis of, or you want to qualify the epoxy that you are going to use in your next product, that can be done at this location.
Okay, I think we have time for one more question. What's next on our list of questions? Can hydrogen and helium be distinguished? This came from a viewer, and I will let you have at it.
Yes, and I think the simple answer is going through our scans. And here what I did is put the scan for hydrogen calibration and the scan for helium. And as you can see, hydrogen result into 1 H plus, which is 1 mass 1, and mass 2, H2 plus. And you can see this 2 peak is due to hydrogen, and that ends near almost at 3, somewhere in this region. And if you look at the helium peak, which is into, it starts from 3.45 to 4.43 AMU, centering around somewhere 3.95 or 3.98. So we have this mass spec has the resolution to differentiate between these two mass specs, hydrogen and helium. And now it also depends on what's the signal strength for helium and hydrogen. If they are very high signals, then it is quite possible that the tail end of the peak would overlap with each other. But for the range of let's say 100 ppm to 20%, 20 volume percent, we can resolve between helium and hydrogen. Yes.
Okay, well, thank you for answering that question. I believe we need to skip down to the next to last slide. For the questions that we didn't get to, we will answer those privately through email. But just to make a couple of points about why you would want to choose Eurofins EAG laboratories, there are several reasons, but I think it's important to state right at the top that client confidentiality is core to our business. We're a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. And I want to thank everybody, and I'm going to turn this over to Dina to close out the webinar.
Thank you both. And also thank you to everyone for attending today's Ask the Expert webinar. If we didn't get to your question today, we will be following up with you soon. If you have any other questions, please send them to the email address on the screen. Once you leave today's webinar, you will receive a survey on the presentation, and we would greatly appreciate it if you would complete the survey and provide your feedback. Please be sure to register for our upcoming webinar. Our next one is on April 5th. It is another Ask the Expert on XRD. I have placed the link in the chat for your reference. And on behalf of Eurofins EJ Laboratories and our expert today, Infrona, I would like to thank you for joining us and have a great rest of your day.